the idea that, again, I mean, this isn't hunter-gathering. I mean, we're solving problems. We're saying, can you take a picture of the black part of a black hole? Can you actually see the light area, the event horizon getting sucked in? I'm talking about the Event Horizon Telescope, not a NASA mission. But, there were times in my life, like when I first saw that picture come together, and I didn't think they'd be able to do that. I don't think people really understand what happened there. They were doing something right on the fuzzy edge of physics being possible. You need to catch the same front of a wavelength of light, right? So light's coming by, it's a wave, it travels at the speed of light. The wavelength of light is tiny. Let's say for a minute, they were dealing with microwaves, so let's say like a millionth of a meter. So something that's a meter divided by a million is traveling past you at the speed of light. And the Earth is round, and the Earth is moving, and they had these 8 observatories all around the planet. And they had to catch that same wavefront, the same one. If it was one wavefront later, one millionth of a meter later, traveling at the speed of light, they wouldn't have gotten the image. They needed to catch the same wavelength, the same photon, the same wave of light had to be caught in all of those telescopes at once. One was at the South Pole, somewhere in the United States, somewhere in Chile. They were all over the planet. And if you caught the same frickin' wave of light.
Here it is.
There you go.
Wow.
They managed to make a telescope that's actually as big as the Earth. And they were able to take a picture of the dark parts of a black hole. Now that's something called the shadow of the event horizon. It's basically the event horizon where time and space stop. We don't even know if there really is an interior to a black hole. All the equations blow up. Time and space don't exist in there. And light, nothing can escape that darkness. The black spot you're seeing there is a little bigger than the event horizon itself. It's called the shadow of the event horizon because time and space are bent around the black hole. And so some of the light that actually gets sucked in is light that would have gone around the black hole. It gets sucked into the back end of the black hole. Literally space and time curve around the black hole. And so that dark part is actually a little bigger than the event horizon. It's called the shadow of the event horizon. And they said they were going to go take a picture of it. And I was like, you have to catch the same wavefront of light in all of these telescopes. I mean, that's going to depend on the height of the mountain, how fast that part of the Earth is moving. They did it. They fucking did it. And they didn't do it just once, right? And, and now we can take a picture of an area right in front of your eyes where space and time doesn't exist. I mean, to a lesser extent, one of the NASA missions that I thought was just spectacular was a small, inexpensive mission called NICER. You're like, who's the NICER person? NICER, N-I-C-E-R. It's the Neutron Star Interior Composition Explorer. And a neutron star, you probably know about these, but when a star dies and the nuclear reactions inside a star cease, all of that gravity of this massive object comes crushing in. And it'll create an object sometimes called a neutron star. They're about 20 miles across. But they have about twice the mass of the sun. And we study many of these at NASA. They're all over the place. They're real. They're something you can take an image of. You can take a picture of. And these neutron stars have physics that we don't understand. You take 2 times the mass of the sun, you crush it into 20 miles. We know that we can't describe the interior of that thing yet. We don't have the physics that matches that type of density. And this crazy little contraption, I mean, it's about the size of a washing machine. It was built in a lab just on the floor that I used to work at NASA. It's cheap, easy to make. I shouldn't say easy, but I mean, it's actually able to create maps of what the surface of these objects are like. They're 20 miles across. They're thousands of light years away. And you can actually create a map of what the temperature is like. And one of the things we see on these maps is the distortion where space and time curves around these objects. They rotate very fast, and there are hot spots we see coming in and off the neutron star. But then as the hot spot goes behind the star, the light bends up and over, and we can actually still see the hot spot because space and time are bending around these objects. You can see that. That's not a mathematical simulation. That's not a theory. You can see space and time bending around these objects. You can see space and time bending into that event horizon. I mean, it's absolutely crazy what we've been able to do. And whether it's a huge project like the Event Horizon Telescope, where I would have bet that they would not have been able to make that measurement, and they did. You know, there were so many hard drives of data. One of the telescopes was at the South Pole, and you wanted the telescopes to be as far apart on the Earth as possible, because then you could basically make a giant telescope the size of the separation of these telescopes. And there wasn't there's pretty good email links down to the South Pole, but the email link wasn't fast enough for all of this data. They sent back literally, there was a ton of hard drives to actually, they had to play them all at the same time and make sure they caught the same photon. If they had caught, seriously, one photon following behind the other, the image wouldn't have worked. They had to catch that same photon. You know, humans are incredible.
Some of us.
Oh, hey.
Some of them, I should say.
Maybe pretty much all of us in different ways.
Yes.
I mean, you know,
unrealized potential.
No, I got to go back to this. I mean, one of my I have 3 friends now who won the Nobel Prize, which is always like, what the hell am I doing?
That's awesome.
But
good friend group.
Yeah.
But you have good group chats.
Well, see, the funny thing is, we certainly don't all get together and talk theoretical physics. I mean, that's not really what we do. But I was seated next to one of them at a meal one time, and somebody came by and said, "Oh, look at all the brain power here." And I actually, I try to be kind of nice about it, but I said, you know, there's a single mother working 3 jobs part-time, you know, who's waiting tables over there. And I mean, the mental capacity and the strength of that person is something that, you know, I mean, don't look at us. Go praise that person.
Well, that's brain power too. It's just a different thing.
It's survival. I mean, it's trying to keep your life and soul together.
Yeah.
The privilege of being able to work at NASA and to be able to work with a team like that and do things you think are impossible. You know, that was kind of a part of my life you could stick a pin in and say that meant something. You know, that gave me some meaning. That gave me joy. And as you said, it's not so much being a hunter-gatherer. It's you know, can we ask a question that we think is impossible, and can we just go and do it?
Yeah, the ultimate expression of human curiosity. When you say that we don't have the physics, when you're trying to understand what's happening in a neutron star, what do you mean?
So you can measure how big these things are, and you can measure how massive they are. And so then you can do a calculation as to what the density inside would be. And, you know, probably the interior core is denser than the outer regions, but if you had a teaspoon of this material, it would have about as much mass as Mount Everest. And the reason they're called neutron stars is that the gravity is so intense on these things. I hate sort of a simple view of atoms as little balls going around each other, because they're not. They're waves of energy. But the gravity actually crushes the electrons into the nucleus. They combine with protons to become neutrons. So they're mainly little balls of neutrons. But we do, there you go. You see the big question mark there at the core. So here's the problem. You run our basic laws of physics, our understanding of how particles work. And you get to the density of a neutron core, and the equations don't work. They're not making the right predictions. We can tell that there's actually a really great NASA video I would suggest you watch. It's called the interior of a neutron star. Well, I can help you find it, but it basically says that the models we have about how matter works at that sort of density, none of them give the right predictions for the size of the neutron star.
Why is that?
We don't have the right physics for it yet. So you know, we run our physics and we say, if you have this much volume and this much mass, what should that interior be like? And none of our current models of how matter works gives us the right observations, gives us the right size.
So what are we missing?
Well, for one thing, you know, what you're probably looking at inside a neutron star is some type of interaction of quarks, the actual sort of building blocks of neutrons and protons, the particles that make up protons and neutrons.
Ooh, that's cool.
Yeah, you got it. You're amazing. I have to say, I'm seriously impressed by this person's ability. Yeah. So, I mean, this is a video that it was done by NASA, testing matter's limits. It's a 4-minute video, and while I don't think it's an absolutely perfect video, I think it's fantastic. And so you see this is supposed to represent the electrons being pulled into the nucleus and making neutrons. And then at the very heart of these things, we're in a state of matter that we have no description for yet. We can't tell you how it behaves. We've never created it in a lab. We don't know how this type of matter acts. It's a new state of matter. We don't know what it's like.
Wow.
And It's made when one of these giant stars explodes. The core of the star becomes compressed, and then this will take you through us trying to figure out whether you have particles as discrete particles, as neutrons and protons, or whether there's some type of quark soup inside. But pretty much every model so far doesn't match what we actually measure from these things. We cannot describe them yet. We need better physics.
Are there any other structures that are similar in our lack of understanding of them in the universe?
You got two big ones right in front of you: neutron stars and black holes, right? So I mean, black holes as well. What is inside a black hole? Is there an inside if space and time don't really exist? And then much more easy to see are these neutron stars. The people who study neutron stars at NASA, they had this wonderful expression. They're like, with a black hole, you can't see anything. It collapses into an event horizon. Nothing's coming out. With a neutron star, you got the frickin' thing right there in front of you. You can actually observe something. And so, they figured that neutron stars are much more exciting than black holes because you can actually do experiments, take a picture, build a telescope. And but this experiment was an inexpensive, small observatory that's up on the International Space Station. And I mean, they're doing incredible work about the nature of physics and testing where our limits are. It's unbelievable what you can do with even a relatively inexpensive mission.